Okay, so let's see the following example. So example 8. Let T the set of all functions from R to R where R is a set of real numbers as in calculus. F plus G and F times G are functions defined by F plus G at the point X is equal to F of X plus G of X, and F times G at the point X is equal to F of X times G of X. And you can readily verify that T is a commutative ring with identity. The zero element is a function h given by h of x is equal to 0 for all x inside of R, and the identity element is the function E given by E of x is equal to 1 for all x belonging to R. So sometimes we would like to have in Zn we have two elements that are not 0, such as 2 and 3. In Z6, when you multiply them, you get 0. But we would like to have rings where this property doesn't happen, where if you multiply two numbers and the product is 0, then one of the two numbers is 0. So what is happening here is that like it detects a hole, like integral domains, like detect like if a hole exists, or if something diverges, then for sure we have a divergent multiplication to begin with. So this is essentially the property of the integral domain. So let's write it down. So an integral domain is a commutative ring R with identity one or that is not 0 that satisfies the following axiom. What is that axiom? Whenever A and B belongs to R, or belongs to the ring R, not R as the real numbers, and AB is equal to 0, then A is equal to 0R, or B is equal to 0R. So we have also the following axiom as well, which is the field axiom, which tells you that any equation of the form A times X is equal to 1 has a solution. So every element can be invertible in a field. Every element is invertible. So we have the following definition. A field is a commutative ring R with identity one R, which is not the 0 ring that satisfies this axiom. For 12, for each A not equal to 0 or in R, the equation AX is equal to 1R has a solution in R. So that being said, we can also define the Cartesian product of two rings, where if you have two rings, then you can define a bigger ring which contains both, so to speak, or it has the graph of both at the same time. So let's try to see what is that theorem about. So we have theorem 3.1. Let R and S be rings. Define addition and multiplication on the Cartesian product or S by R and S plus R prime S prime, which is equal to R plus R prime and S plus S prime, and R and S R prime S prime, which is equal to R prime S prime. Then R cross S is a ring and if R and S are both commutative, Then so is R cross S if both R and S have an identity. Then so does R cross S okay. I'm just making sure about something. Yeah, okay. Good. All right. We'll be doing the following result as well, which is about subrings. All right. So theorem 3.2. Suppose that R is a ring and that S is a subset of R such that S is closed under addition okay. Yes, the second thing, S is closed under multiplication. Multiplication. Zero. R belongs to S. And the fourth thing, if A belongs to S, then the solution of the equation A plus X equal 0 R is in S. Then S is a subring of R. Okay. So we'll have the following example where I will say this example and then I will be closing things. So the set Z square root of 2, which is equal to A plus B times square root of 2, where A and B belongs to Z, is a subring of R. Yes. So I'll just leave it as an exercise for you guys to do, and I'll close this video now. Thank you so much, and I'll see you in the next video. Bye now.